Welcome to Deep Dive, where we explore the deep ideas and advanced concepts shaping our understanding of reality. I'm Ben, and today, we're taking on a journey into the mind-bending world of quantum computing, and we're going beyond the basics. From how scientists harness single photons to create quantum states to the fundamental ways quantum mechanics could change how we view reality itself. Let's dive into what it really means to work with quantum particles as information carriers, why this is so powerful, and how it challenges our deepest assumptions about computation, nature, and even the universe. Let's start our podcast with the innovation of a single-photon qubit machine and why this is important. To understand how quantum computing works at a fundamental level, let's start with an example from the lab, a single-photon qubit machine created by Professor Chih-sung Chuu and his team at Tsing Hua University in Taiwan. Recently, a scientist in Taiwan managed to produce a machine that controls individual photons, each representing a single qubit. Now, why is this so important? Well, photons are quantum particles that can exist in different states that can represent 0, 1, or a superposition of both. A single-photon qubit machine is unique because it allows researchers to work with the smallest units of quantum information. Each photon can be split and manipulated in carefully controlled experiments, using something called a beam splitter. Imagine a photon traveling through a splitter. It splits into two possible paths, each representing a potential state. As long as we don't measure it, it exists in a superposition of both paths. When we measure it, however, it collapses into a single path, either left or right. This property is foundational to how quantum computers perform calculations. But this also means that creating a machine that can control a single photon is challenging, especially when so many environmental factors introduce noise that disrupts this delicate quantum state. Now, let's move on to visualizing quantum registers and beam splitters. Imagine a machine that can hold and split photons, directing them into two distinct pathways. These pathways are like the registers in classical computing, where data is stored temporarily. However, unlike classical registers that only store binary values, 0 or 1, quantum registers can hold values in superposition. When a photon hits a beam splitter, it's directed into multiple paths simultaneously, and these paths represent various potential states. Each pathway could be thought of as a register that temporarily holds information about the photon's state. By arranging a series of splitters and mirrors, scientists create controlled environments where photons can exist in these probabilistic states without collapsing. And yet, there's a catch. Any interference, like a temperature fluctuation or stray particles, can cause a qubit to lose its quantum state. We call this decoherence, and it's why quantum computers must operate in controlled environments. Even a small change in temperature can make it impossible to capture these delicate quantum states reliably. This experiment shows how incredibly sensitive quantum systems are and why they're so powerful yet challenging to work with. Now, let's explore the limitations of classical thinking in quantum experiments, and here's where things get tricky. As advanced as we are, our thinking is still rooted in classical physics. This classical mindset expects binary outcomes, true or false, 0 or 1. We struggle to accept quantum states as they are, probabilistic and fluid. So, when we observe noise in these quantum systems, we register it as an error, something out of our control, rather than seeing it as part of a complex, probabilistic system. You see, in classical experiments, we expect predictable outcomes under controlled conditions. But in quantum computing, what we often call noise might not be errors at all. It could be additional information that we're just not equipped to interpret. For instance, if we introduce even a slight change in temperature, we see it as adding unpredictable noise. However, if we could develop tools to capture and interpret this additional data, these fluctuations might actually reveal new quantum states. In essence, our classical mindset forces us to control what we can't predict. If we instead adapted to a model that works with probability as a feature, we might unlock much more of quantum computing's potential. Now that we're on the same page about quantum registers and the challenges of classical thinking, let's reimagine quantum computing as moving beyond binary code to something more like equations as code. Instead of fixed values like 0 and 1, quantum systems work best when we think of them probabilistically. This shift could allow us to create algorithms not as rigid sequences but as dynamic equations that guide and adjust the probabilities of quantum states. Here's where machine learning comes in. Imagine training machine learning models to tune and optimize these equations, effectively guiding quantum states toward desired outcomes. By analyzing and learning from thousands of quantum states, machine learning models could adjust parameters like phase, amplitude, or superposition probabilities to find the most efficient pathways for complex quantum problems. This process could work almost like real-time troubleshooting for quantum computations. Every run would help the model learn how to better navigate quantum states, tuning itself as it learns which variables best amplify the desired outcome. With AI handling these probabilistic adjustments, quantum algorithms could become incredibly adaptive, maximizing the potential of each qubit and helping us bypass the current limitations of noise and decoherence. But AI's role doesn't stop at optimization. Advanced AI could help write these equations as code directly. By recognizing patterns and relationships in quantum data, AI could suggest entirely new quantum algorithms, even discovering pathways human programmers might overlook. The potential of AI to innovate in quantum computing goes beyond simple parameter adjustments. It opens the door to creating whole new types of quantum logic. If we bring AI into quantum computing as a core component, we're effectively developing a partnership where quantum systems generate possibilities, and AI helps us steer these possibilities toward meaningful outcomes. Quantum machine learning models would act as guides within the quantum realm, continually refining the equations and adjusting to the probabilistic landscape. Imagine an AI that doesn't just execute quantum calculations but learns how to interpret and refine them on the fly, making quantum systems more powerful and flexible than ever before. In a sense, this combination of quantum computing and AI could lead us to the point where we're no longer forcing quantum systems to fit classical constraints. Instead, we're building flexible, probabilistic systems where equations act as adaptive code, all guided by AI. It's a system that doesn't just compute, it explores, learns, and potentially redefines what computation even means. Let's take a deep breath as we have discussed so deep and so far into this cosmic quantum adventure. Okay, good, let's move on to cosmic code and the boundaries of our universe. Here's where things get profound. If quantum computing pushes us to accept probability as a core feature, what if the universe itself works the same way? Let's imagine that the universe is like a massive program, running across countless ranges of possibilities, each range containing infinite possibilities within specific boundaries. Think of it like this: between 0 and 1, there are infinite numbers. You have 0.1, 0.01, 0.001, and so on. Each one brings you closer to 0, but you never quite reach it. Similarly, you can have infinite steps between 1 and 2, or between 2 and 3. Even though each range has infinite possibilities, it's still contained within specific boundaries, like 0 to 1 or 1 to 2. This is the idea of bounded infinity, infinite variety within finite limits. No matter how advanced we become, even if we were a Type 8 civilization mastering every particle, force, and galaxy in the universe, these boundaries would still confine us. The rules of this cosmic program define what's possible, setting boundaries that can't be broken, only expanded within each range. And here's a mind-bending idea. Beings outside our universe, let's say in higher dimensions, might look at our universe as a structured program. To them, what appears probabilistic or unpredictable to us might be as simple and deterministic as a program running from start to finish. From their perspective, the entire program of our universe, including events like life, death, and even the formation of stars, could appear as predictable states, each unfolding within the infinite possibilities defined by cosmic boundaries. In this last but not least segment, let's talk about classical limitations versus cosmic programs. This brings us full circle. Even as we build quantum computers that transcend binary constraints, we're still confined by classical perspectives that seek control and predictability. Just as we label anything we can't control as noise, civilizations, even as advanced as a hypothetical Type 8, would still be bounded by the universe's cosmic code. Outer dimensional beings, however, might operate beyond our deterministic boundaries. They might see universes as subsets of a larger system, like different programs on a universal platform. To them, our universe's limitations would seem primitive, just as our classical mind still struggles to fully grasp the fluid, probabilistic nature of quantum computing. So, to wrap up, quantum computing doesn't just offer us a new kind of machine. It challenges us to rethink what computation, probability, and determinism really mean. When we imagine equations as code, we're tapping into a structure that may not just apply to technology but could reveal something fundamental about our reality. Whether or not our universe is part of a larger, deterministic system, quantum computing pushes us to see beyond binary constraints. It's a world where infinite possibilities exist within finite boundaries, a boundless reality with boundaries we're only beginning to understand. Thank you for joining me on this thought-provoking journey and deep dive. If you're interested in exploring more questions at the edges of science, technology, and philosophy, make sure to subscribe to our YouTube channel. Don't forget to like this video as it helps us a ton. You could also share this video online and elsewhere to help spread the knowledge about quantum computing. I'm Ben, and until next time, keep questioning, keep exploring, and keep diving deeper.